So we have about 10 minutes left. And in this 10 minutes, I cannot prove the remaining theorem, but I can tell you about it. And that's a very, very, very important theorem, especially for quantum mechanics, also for mathematics. And you may have come across this theorem in some linear algebra course or algebra course. And if not, you know, it is my privilege to tell you about it. And this is called Shur's lemma. It's an extremely powerful lemma. There are several Shur's lemma, but you know, we're just going to be proving just one. I think so, yeah. Okay. So the idea is this. Suppose D is an n-dimensional irreducible representation. Let me remind you, we are going to use the word irrep for irreducible representation of a group G just one second. Okay, yeah. So, and B is a matrix such that B commutes with all the elements of this representation. Okay. Then B must be proportional to the identity matrix. Okay. Okay, so suppose I give you a representation of a group which is irreducible, meaning that it cannot be broken down into smaller parts, right? So when is a representation reducible? When you can find a similarity transformation such that the representation takes this form, right, for all G's. So if this is not possible, then that representation is irreducible. Now, if there exists another matrix B such that it commutes with all the elements of the representation, then B must be proportional to the identity matrix. And often it turns out this constant of proportionality is a very important mathematical or physical quantity. Okay. So those of you who have done quantum mechanics, so let me make a comment. I don't want to attempt a proof today because we are almost out of time. But those of you who have seen quantum mechanics, you know that the angular momentum operator is a set of three matrices, J1, J2, and J3, right? But the square of the angular momentum operator is J squared, and that operator actually commutes with all the J's. And therefore, J squared is actually proportional to the identity operator, where the coefficient is the square is the related to the square of the, where J is it's the total angular momentum eigenvalue, right? In units of h bar. I'm putting h bar to 1. So, but in units of h bar, this is the total angular momentum. So J squared become, so that's an application of Shur's lemma. Okay. So, okay, I'm just going to like take the well, I mean, I'm not sure, did everyone get the message? I think so, yeah, everyone is here. So let's take the attendance and then we can have some questions, okay? Also, are people okay with tomorrow being the third graded quiz? I mean, I know
for me, Friday would have been much better time. Like
I can do Friday. It's actually better for me if I do it on Friday.
That would be nice, sir.
Yeah, I agree.
Okay,
That would be better.
Okay, Friday. It'll be easy. It'll be half an hour long. You know, yeah, you just do it. Okay, Friday it is then. Okay, Rahul is here because he was the first person to show up today. Zabir. No, Zabir. Dipro, I think I saw Dipro, yeah. Medad. Yashan.
Yes, sir.
Shujosh, I saw Shujosh. Sitima.
Present, sir.
Yeah. Audrey.
Present, sir.
Okay. Saif is here. Abdullah.
Yes, sir.
Okay. Nahi is here. Okay. Fiza.
Here, sir.
Okay. Fahim.
Present, sir.
Okay. Farhan. Oishik. Proma. Okay, so I've been a little bit behind in posting my lectures because my software was not working, but it's working now. I made it work. So hopefully it'll be posting again soon. So any questions from today's lecture? Okay, so if not, thank you again. And we shall see you tomorrow at 6:40 for the special relativity lecture, okay? Now that's optional, of course, you don't have to come, but if you want to come.
Goodbye, sir.
Okay, thank you.
Sir.